Every nuclear reactor on Earth depends on metals that can withstand extreme heat, radiation, and chemical attack. Inside a reactor, temperatures soar to over 1,000 degrees while radiation bombards every surface. Ordinary metals would break down, corrode, or even disintegrate over time. This is why nuclear power relies on a select group of materials, metals that don't just survive, but allow reactors to function efficiently and safely. But what are these metals? How do we extract and prepare them for use? And why are some of them absolutely essential for nuclear energy? Today, we explore the metals that make nuclear reactors possible. At the core of every nuclear reactor is uranium. But natural uranium isn't ready to be used as fuel. It has to be extracted, purified, and processed. Uranium is mined from deep underground or open pit mines, where it is found in minerals like uraninite and pitchblende. The raw ore is crushed into fine particles and treated with acid, which dissolves the uranium while leaving other minerals behind. This solution is then processed to extract pure uranium compounds, which are dried into a yellow powder known as yellow cake, chemically known as uranium oxide. But this yellow cake still isn't usable as reactor fuel. Natural uranium contains two isotopes, uranium-238, which makes up over 99%, and uranium-235, which is only 0.7%. The problem is, only uranium-235 can sustain a chain reaction in a reactor. To make nuclear fuel, uranium must be enriched, meaning the proportion of uranium-235 is increased. To do this, uranium oxide is first converted into a gas called uranium hexafluoride. In enrichment plants, this gas is fed into high-speed centrifuges that separate the slightly lighter uranium-235 from uranium-238. After multiple stages, enriched uranium is converted back into a solid, pressed into small ceramic pellets, and packed into zirconium tubes to form nuclear fuel rods. These rods are then loaded into a reactor, where they will sustain a controlled nuclear reaction for years. Plutonium is another metal that can power a nuclear reactor, but unlike uranium, it doesn't occur naturally in significant amounts. Instead, plutonium is produced inside the reactor itself. When uranium-238 atoms absorb neutrons, they can transform into plutonium-239, which is fissile, meaning it can also sustain a chain reaction. This means some nuclear reactors can actually breed their own fuel, turning uranium-238 into a usable energy source. To extract plutonium, spent nuclear fuel rods are removed from the reactor and chemically processed. The most common method is the Purex process, short for plutonium-uranium redox extraction. This process dissolves the fuel in strong acids and separates plutonium from uranium and fission byproducts. The recovered plutonium can then be mixed with uranium to form MOX fuel or mixed oxide fuel, which is used in some reactors today. While uranium and plutonium provide energy, another metal plays a critical role in nuclear reactors, zirconium. This metal is not a fuel, but without it, a nuclear reactor wouldn't function properly. Inside a reactor, uranium fuel pellets are stacked inside long metal tubes. These tubes need to withstand extreme heat and radiation, but at the same time, they must allow neutrons to pass through freely. Most metals would interfere with the nuclear reaction by absorbing too many neutrons. This is where zirconium comes in. Zirconium has one of the lowest neutron absorption rates of any structural metal. This means it can safely hold nuclear fuel without disrupting the reaction. Extracting zirconium is a complex process. It is found in zircon minerals, which are often mined from beach sands in Australia and India. After separation from other minerals, the zirconium is converted into zirconium oxide, which is further refined into zirconium tetrachloride. To get pure zirconium metal, the Kroll process is used, where zirconium tetrachloride is reacted with molten magnesium, producing zirconium sponge, which is later melted and shaped into nuclear fuel cladding. Zirconium and hafnium are nearly identical chemically, making them difficult to separate. However, their nuclear properties are completely opposite. While zirconium allows neutrons to pass through, hafnium absorbs neutrons extremely well. This makes it a terrible choice for fuel cladding, but a perfect material for control rods. Control rods are inserted into reactors to absorb excess neutrons and regulate the reaction. If a reactor is producing too much energy, control rods can be inserted deeper to slow things down. If more power is needed, they are pulled out to allow more neutrons to interact with the fuel. But before zirconium can be used in fuel rods, all the hafnium must be removed. This is done through multiple refining steps, such as solvent extraction and fractional distillation, separating the two metals with extreme precision. The purified zirconium is then shaped into reactor components, while the extracted hafnium is used in control rods, completing the delicate balance of nuclear reactor operation. Every nuclear reactor is built around a carefully chosen combination of metals. Uranium and plutonium provide energy. Zirconium protects the fuel while allowing the reaction to continue. Hafnium absorbs neutrons to keep the reactor under control. Nuclear metallurgy isn't just about making energy. It's about designing materials that can survive the most extreme conditions known to science. These metals, uranium, plutonium, zirconium, and hafnium, aren't just the foundation of nuclear power. If you like this video, give us a thumbs up and subscribe. And if you have any suggestions for further videos, add it in the comments. Goodbye!